Did you know not every topological space can be described using distances? But under certain conditions, we can guarantee a topology comes from a metric. Today, we'll explore one of the most powerful results in topology, the Nagata-Smirnov metrization theorem. These figures illustrate the baseline of a metric space. The distance function gives us rigid, predictable basis elements, like the circular regions in figure 13.1, or the rectangular ones in 13.2, which act as the geometric foundation for the topology. Compare that to this diagram of a general topological space. Here, distance is absent. The open sets are just abstract collections that satisfy the three core axioms, taking on entirely non-geometric configurations. This creates the metrization problem. If handed an abstract topological space, we need to know if a hidden distance function generated those open sets. We have to identify the exact topological fingerprints left behind by a metric, proving its existence even when the function itself is missing. Preparing for advanced exams like CSIR NET or GATE, this is a vital diagnostic skill. You must be able to determine if a space is well behaved enough to support geometry without having to construct a metric from scratch. The standard entry-level tool for this check is Urysohn's metrization theorem. It guarantees metrizability if a space is regular and second countable. The bottleneck is that second countability requirement. Demanding a strictly countable basis is a massive restriction, and many perfectly valid metrizable spaces fail it. This table of contents points to our solution in section 40. We need a framework capable of handling uncountably infinite collections of open sets, provided they aren't pathologically clustered. To get there, we must search for a property that tames infinity. We do this by examining the space locally rather than globally. The Nagata-Smirnov theorem provides that exact necessary and sufficient bridge, proving exactly when abstract sets can support a true distance metric. The primary core mechanism for controlling infinity within a complex topological space is a property called local finiteness. A collection is locally finite if every point has a neighborhood that intersects only finitely many elements. Think of this as a mathematical safety valve. A collection can be infinite globally, but remains safe because it appears finite locally. Consider the real number line covered by open intervals from n to n+2, stretching infinitely in both directions. If we test a point, say 1.5, and draw a small neighborhood around it, it intersects only two sets, the interval 0, 2 and 1, 3. Because this applies to every point, the collection is locally finite. This property allows us to calculate local features, like distances, without blowing up into an undefined infinite sum. To see what happens when this fails, look at the collection of nested intervals from 0 to 1 over n. For a non-zero point like 0.5, it behaves perfectly. The intervals retreat past it, so a small neighborhood hits only a finite number of sets. But the critical failure point is exactly at 0. Any neighborhood drawn around 0 contains an infinite number of intervals. This is a common exam trap. Failing the condition at just one single point invalidates the local finiteness property for the entire collection. Distance metrics cannot exist in the presence of this kind of infinite clustering. The distance to the cluster becomes mathematically ill-defined. Controlling infinity is half the battle. The second pillar of the theorem is regularity. A space is regular if you can separate any point X from a closed set B using entirely disjoint open neighborhoods. This strict separation is the topological requirement for building continuous functions, as proven by Urysohn's lemma. Distance itself is a continuous function. If you can't separate a point from a closed set, you can't assign a meaningful non-zero distance between them. Regularity provides the geometric resolution needed to distinguish between different parts of the space. We now have the components to formally state the Nagata-Smirnov metrization theorem. A space is metrizable if and only if it is regular and has a basis that is sigma locally finite. The prefix sigma simply means a countable union. A basis is sigma locally finite if it can be constructed by unioning together a countable number of locally finite collections. This enables a stitching process. Local finiteness allows us to combine many local distance functions into one global metric without infinite sums causing interference. For technical exams, note that any countable basis is automatically sigma locally finite. This shows exactly why Urysohn's earlier theorem is naturally contained within this one. Nagata-Smirnov is the definitive structural scan of a metric space. If these two properties exist, a metric must exist. Let's apply the theorem to two spaces that appear similar but behave entirely differently. The standard real line is regular, and it has a basis of rational intervals. Since the rationals are countable, the base is countable, perfectly satisfying the sigma locally finite requirement. It is metrizable. Now look at the Sorgenfrey line, which uses half-open intervals. While it is regular, any basis for this topology forces uncountably many elements to cluster against every point from the left. This creates a dense, non-finite overlap that no amount of unioning can resolve into a locally finite collection. Because it fails to produce a sigma locally finite basis, the Sorgenfrey line is a space where the local infrastructure for a metric is mathematically impossible. Understanding these failures prevents you from searching for metrics in spaces where the lack of local finiteness forbids their existence. For metrization questions in exams like GATE or IIT JAM, follow a strict three-step decision tree. Step 1, is it regular? Step 2, is it second countable? Step 3, if it isn't second countable, can you find a sigma locally finite basis? If you found this explanation helpful, don't forget to like the video and subscribe for more book-based mathematics explanations. Thanks for watching, and we will see you next time. The Nagata-Smirnov theorem proves that metrizability isn't a mysterious quality. Instead, it is the logical result of how a space separates its points and organizes its infinite collections.